Okay, so now we want to answer this question that how does the pressure in a fluid vary from point to point? Okay, so we know the Pascal's law, which is the pressure at a point in a fluid is independent of direction as long as there are no shearing stresses. So let's see how the pressure varies from point to point in a fluid. So in order to answer this question, I'm gonna draw a free body diagram of the flow. Fluid element. Okay, so this is X, Y, Z direction, the coordinate system. These are the unit vectors. I, J, and K. Okay. So now the fluid element, let me draw that one. A fluid element here we have okay, so this is a fluid element, and now I want to write the pressure forces that are exerted on this fluid element. Okay, so and also all the forces. So let's start. This is surface and body forces on a small fluid element. So the first body force is the weight of the fluid element itself, right? So if this is the center, I'm just gonna show that as the body weight. So this is what we call, and this point in the center, I'm just gonna call it P, which is a point in the center of this fluid element. And so this one is gonna be, this point is gonna be the body force or weight of the body force or weight, right, of this fluid element. Okay, and now I want to calculate the forces around this for this fluid element. So the first one is the pressure, right? So say the point here for the in the middle has a pressure of P, which I showed here, right? And then I want to calculate the pressure, say from here in this side. What is going to be the pressure force on this fluid element? Okay. So if you remember from this calculus formula of Taylor series here, okay, so if I want to show this from just YZ plane, okay, let me just draw it in YZ plane so you better understand what we have here. So in YZ plane, we have this P point here, which is the pressure at the center of the fluid element, and then we want to see what is going to be the pressure here. Okay. So from this Taylor series expansion that we learned, we found that we can write the function, any function, in terms of the value at a given point plus its derivatives and then higher order terms. Okay, so I'm going to do the same thing here. So for P, I'm just going to write it as the pressure function is going to be P, say as a function of Y, is going to be P, which is the P at here, plus this difference here, which is delta Y, say delta Y over half, and this is say delta Y. So let me just write this. This is delta Y. This length is delta X. And this length is delta Z. Okay. So it's going to be P, which is the pressure at the center, plus what? Here we have F prime A, which is going to be the derivative, partial derivative of P with respect to Y, because here we are writing it in the Y direction, times, so this is the first derivative, times X minus A, which is going to be here Y, say this is Y2, and this is Y1, it's going to be Y2 minus Y1, which is what? Is delta Y over 2, correct? And then plus other terms. So we have like higher order terms. So it's going to be the second derivative. So second derivative of Y with respect to P with respect to Y times 1 over 2 factorial times delta Y square and other terms, right? So if we assume, if we suppose that delta Y is very small number, okay, so then delta Y square is going to be much smaller than delta Y, correct? So I can just suppose and assume that these terms are almost equal to 0, right? Because they are going to be very small to the first order approximation, okay? So for the first order approximation, this is going to be my P here, okay? So I'm just going to write it down here. It's going to be what? Is going to be the pressure. I'm writing the forces, so it's going to be the pressure P plus partial P partial Y times delta Y over 2. And then I have to, because this is a pressure, and what is the definition of pressure? Pressure is force per unit area. So if I want to get force, I have to multiply pressure by area to get force, correct? So I have to multiply the pressure here with the area here to get the force that is acted on this side of the fluid element. So what is the area? It is delta x delta z, correct? So this is going to be the force on the right side. So similarly, you can write the force on the left side. So on the left side of this cube fluid element, we are going to have the same thing, but now the direction is reversed. So instead of for the y2 minus y1, if this is y0, say this is y0, if you write it down, so you are going to have y0 minus y1, so it's going to be minus delta y over half, right? So we are going to have p minus partial p over partial y. Let me write it here because it's going to be easier. So p, pressure at point in the center, minus delta p over the derivative of p with respect to y times delta y over half times delta x delta z, right? So this is going to be the force on the left side. And then similarly, you can write it for other places. For example, for the top, we are going to have what? We are going to have P plus, now it's going to be delta P, or the derivative of P with respect to which direction? We are now moving in the Z direction, right? This is the Z direction. So it's going to be over Z, and we are higher above the point P. So we have to add that times delta Z over half. This is how much we went up, times the area, which is going to be delta X delta Y. So this is the area. And then at the bottom, we have this force here, which is acting on this fluid element. Is going to be P minus delta P over delta Z times delta Z over 2 times delta X delta Y. These are similarly you can find in all the angles on all the sides of this fluid element. These are going to be surface forces, and the only body force here is the weight of the fluid, which we have shown with the blue line here. Okay, so these are all the forces that act on a small fluid element, and in order to approximate the pressure with the central pressure of the fluid, we use the Taylor series, which is here. So this is just Taylor series expansion. And then we got all these different terms. So now I want to calculate the forces. So calculating forces. So in the y direction, I have what? The sum of all the forces in the y direction is going to be what? We have this force, which is on the positive, minus this force in the negative side, right? So we are going to, I'm just going to write it down, P minus delta P over delta Y, or the first derivative of P with respect to Y, times delta Y over 2 delta X delta Z minus this force I'm just gonna write it down here. P plus partial P over partial Y, delta Y over 2, delta X delta Z, which is the area at that site. Okay, so these two terms are going to cancel out. They are the same, P delta X delta Z. So I'm just going to be left with this term, and these two are I'm gonna add them together. So I'm going to have minus delta P over partial P partial Y, and then delta Y half plus delta Y half is going to be delta Y. So I'm going to have just delta Y, and to write it in order, I'm just going to write delta X delta Y delta Z. Okay, so this is in the Y direction. So let's see in other direction. So in the X direction, because everything is also the same, we don't have any additional forces in this direction. It's just a pressure force. So similarly, we get delta Fx, the sum of the forces in the X direction, is gonna be minus partial P partial X delta X delta Y delta Z. Okay, now let's look at Z direction. So Z direction is a little bit different, and let's see why. So the pressure forces are the same. It's going to be similar to the other directions, but we also have this body force which acts in this direction, right? In the Z direction, and that is this weight of the fluid. So I also have to consider that and add that to my equations. So for the pressure forces, we are going to have similarly minus partial P partial Z of delta X, delta Y, delta Z. So these are the pressure forces. And then I also have to add the body force. And because the body force is in the negative side, I just subtract it, right? Because this is the positive side, and then this is the negative, right? So I have to subtract the body force from the sum of the forces. So the body force is going to be what? Is going to be just the weight of this fluid element. So the weight is going to be the density is going to be mg, right? It's going to be the mass times the gravitational force. And what is mass? Mass is rho, the density, times the volume of this fluid element, which is going to be what? It's going to be delta X, delta Y, delta Z, right? So this is mass, and this is G. So this is going to be the weight of the fluid element, right? So this is going to be the sum of the forces for this fluid element, okay, in these different directions. So now I want to define something, a gradient or del vector operator, which is going to simplify my notation. So this is just a notation, okay? So gradient or del vector operator definition. So this is just to simplify the notation. And also, if you see this gradient operator, this is what it means. So the gradient operator, so gradient of any variable, is gonna be defined as this, is the partial derivative of that variable with respect to x times the unit vector in the I direction, which is here, plus the partial derivative of that variable with respect to y times in the j direction, which is here, the unit vector, plus the partial the derivative of that variable with respect to z in the k direction. Okay? And instead of these parentheses, you can put anything. This can be like, for example, this can be x. This can be g, a function g. And any function can be here. This is just an operator, right? It operates on any mathematical variable. So now let's see that some total force on the fluid element is going to be sum of the all forces in different directions. So it's going to be what? It's going to be, first we have the x, the y, x, I'm going to just write first the x one, which is going to be minus delta px. So I'm just going to factor minus. So I have minus partial p partial x. And then this is going to be in the I direction, right? Because I said in the x direction. This is in the x direction, so I need to add this I element, the unit vector. The same thing for y. If y is in the y direction, so I need to add this j unit vector. So it's going to be partial p partial x in the I direction plus partial p partial y in the j direction. This is that one. And then plus this term, which is going to be partial p partial z in the k direction. And I have factored minus and also the volume of the fluid, which is going to be delta x, delta y, delta z. And then I also have this term, which is the body force or weight of the fluid. So it's going to be minus rho g in the k direction times delta x, delta y, delta z, which is the weight of the fluid. Okay? So this is going to be the sum of the or the whole forces or the total force in this fluid element. And so if now you look at this gradient or del vector, you can see this is actually the definition we had. So I can just put it down here. And so this is just the definition of a del vector, a gradient vector, right? So I can just write it down as gradient of P, which is the gradient of pressure, and we call it as pressure gradient. Okay. So I can write the sum of all the forces is going to be what? Is going to be minus pressure gradient plus rho g k, which is in the k direction, delta x, delta y, delta z. So I just factored delta x, delta y, delta z and minus. Okay. So this is the sum of the forces in a fluid element. So it's going to be the pressure gradient in different directions and the weight of the fluid. So these are the forces that we have when we draw the free body diagram. Okay. So now I'm going to just use Newton's second law to find these forces based on the acceleration of the fluid, okay? So this is a very general statement. So the sum of the forces based on the Newton's second law is gonna be m, the mass times acceleration, correct? Mass times acceleration. So instead of mass, I can write density rho. So rho is density times delta x, delta y, delta z, which is the volume. This is going to be mass times a, which is the acceleration of the fluid. Okay? So instead of this sum of the forces, the total force, I'm going to write this one. So I just substitute that. So I have minus grad P plus rho g k times delta x, delta y, delta z equals to rho a delta x, delta y, delta z. Okay, this is just here. So now you see that these two volume under both sides of the equation cancel out, delta x, delta y, delta z. So I am left with this formula in a fluid element. That is minus grad P, pressure gradient, minus rho gk equals to the density of the fluid element or the fluid times a, or acceleration. So this is very important formula. That you need to remember. Because this shows the pressure, the body, for the force balance in a fluid element, which is which consists of the pressure gradient, the body force, the body weight of the fluid, and this is equals to the acceleration in that fluid element. Okay? So remember this one because this is an important formula. And now I want to use this formula to answer my question. So this is the pressure variation in a fluid from point to point, but I want to see this for a simpler case, which is the pressure variation for a fluid at rest. Okay? So pressure variation for a fluid at rest. So for a fluid at rest, we have, for a fluid at rest, for a fluid that is not moving, we have A, or the acceleration of that fluid, because it's not moving, is 0, right? So this formula is going to be simplified. So I'm just going to write it down. So grad P plus rho gk is going to be what? Is going to be rho times A, which is A is 0, so it's going to be just 0. So what does this tell me? So this tells me that because the definition of grad P, I'm just going to write it down here, is as this. So it's going to be delta P delta X I partial P partial Y J plus partial P partial Z K plus rho G K equals to 0. Okay? So in the I direction and J direction, there is no other thing than this pressure gradient. So in the I direction, I have, this means that partial P partial X should be 0. So if I just write it in the J direction, so this means that partial P partial Y should also be 0. That means the pressure is not gonna vary in the X and Y direction, but in the K direction or in the Z direction, the vertical direction, I have partial P partial Z should be minus rho G. And this is a very important formula and the basis of hydrostatics. So let's see, what does this mean? So this means that if we move horizontally from any point to another one, the pressure does not change in a fluid at rest. This is important. So if you have a fluid that is not moving, say for example, you have this tank of water, or you have this say something like a dam or anything, okay? You have this fluid, okay? That is not moving, it's constant. So let me show it here. For example, like it is in a tank of water like this, okay? So this means if you move in the horizontal direction, that means in this direction, the pressure is not going to change. So the pressure here, P1, and here, P2, and here, P3, all of them are equal, because we are moving in the horizontal direction. And this is based on these two formulas. Okay. So this is the first thing for a fluid that is at rest. So if a fluid moves, then the things are going to be different. Okay, so we will talk about those later at the end of this chapter. Okay, but for the fluid at rest, this is what we have. And the second thing is P, or pressure, only depends on Z. So we can write it as the ordinary differential form as follows. So we can just write this as dP over dz equals to minus rho g. So this shows that the pressure only depends on z, the vertical direction, or the depth or the elevation that we are looking at, okay, in a fluid at rest. this is what we found here based on this formula and also from the Newton's second law, and by setting acceleration to 0, okay? So as you see, the pressure decreases as we move upward in a fluid at rest. So this is what this formula says to us. So the pressure decreases as we move upward in a fluid at rest. What does this mean? So it means that pressure of a fluid, say this is a water surface, the pressure at the bottom of the fluid is much higher than the pressure near the surface. So if this is P2 and this is P1, P2 is going to be greater than P1. And the reason is also just intuitively, you can also think about it. For example, in a pool, when you are in a pool, your foot, if you are, for example, standing like this, right, your foot is going to experience a higher pressure than your head, right? And the reason is simple, because there is more water on top of that, right? So here you have this much water on top of this, and so this is gonna add some pressure to the bottom surface, right? But on the top, for example, here you have just this much water, for example, for this surface. So there is not much water. So that is why the pressure at the bottom should be higher than the pressure at the surface. So the pressure decreases as we move upward in a fluid at rest and increases as we move downward toward the surface. Okay? So this was just an intuition of what does this mean. Okay. So now I want to define something called incompressible fluid, a concept that is also what we mostly are going to use in this course. We are not going to work with with compressible fluids, okay? So that is typically for aerodynamics and aerospace engineering, and we don't typically work with those type of fluids. So this is called incompressible fluids, and let's see what is this. So an incompressible fluid is a fluid with constant density. For example, like water or liquids. Okay, so this most of liquids. So this is a definition of an incompressible fluid. So that means that the density is not changing in a fluid from place to place. So for air, for example, you can have some situations where the fluid density is different somewhere from the other place. Also, even in water, you might have some different densities, okay? For example, because of salinity or other things. So incompressible fluid is a fluid with constant density, or it has also some better, more scientific definitions that I'm not gonna go through that. Like we talk about the divergence of velocity and other things. But this is a simpler definition of that, which is the constant density. So this means that, for example, for this equation, dp over dz equals to minus rho g. This is the equation we found here. The density is going to be constant in the fluid, okay? So if we integrate, we are going to have, and also change this. So I'm just going to write this as dp equals to minus rho g dz, okay? Then if I integrate from one place to another place, so I'm going to have, for an incompressible fluid, P1 and P2, dp, this is going to be the left-hand side, so I integrate from both sides, okay? This is how you do integral. Then I'm going to have this is going to be the left side, and then the right side is going to be minus integral of z1 to z2 of rho g dz. Okay, and because I assume an incompressible fluid, so this is going to be constant for incompressible fluid, right? It's not going to change. So I can just take this out of the integral, and g is also constant, so I can also take it out of the integral, and write minus rho g from z1 to z2 of dz. Okay, so this one is what? The integral of this is just 1, so it's going to be P2 minus P1 equals to minus rho g, and then the integral of this is going to be what? Is going to be similarly z2 minus z1. Okay, this is the integral from 2 points, for 2 points in a fluid. For example, you have point 1 here, and then you have point 2 here, and it has z1 and it has z2, right? I'm just taking the integral for any 2 arbitrary points in a fluid, because I want to see the pressure variation in a fluid from point to point. And that was our original question. So this gives us a hydrostatic distribution. Hydrostatic distribution. And that is P1, pressure at point 1, equals to rho g z2 minus z1 plus pressure at point 2. This is very important formula, and it comes from the integration of this one. Integration of this one. If you integrate this, we are going to get this hydrostatic distribution, which is this simple formula. And what is this? This is just an elevation difference, right, between 2 points in a fluid element. So here we had, right? So for example, one here, one here. This is going to be Z2, and this is going to be Z1, and this is going to be Z2 minus Z1 is going to be H, right? So this is the distance between 2 points. So this is H, or the height difference or distance between 2 points. So what we see here is a very interesting point, and that is pressure varies linearly, right? This is Z or H. This is not Z squared. This is Z, right? So this is a linear relationship. So pressure varies linearly with depth if we assume h is depth, so it's rho gh plus p2, right? So this h is linear. So it's not h squared, it's not varying like that. With depth for what? And these are the assumptions for an incompressible fluid at rest. These are the assumptions we made. Incompressibility, that is, density should be constant. And also, the fluid is at rest. So it's gonna, if you have a fluid at rest which is incompressible, so most of the fluids we study are incompressible, for example, water. And then if it's at rest, it doesn't move, then the pressure is gonna vary linearly with depth. Okay? So for example, say we have here water, and this is the free surface of the water, and this is what the symbol we are going to show, the free surface, okay, from now on. If you don't remember, just try to recall it. And then I want to write the pressure distribution for this fluid at rest, which is water. This is x, y, and this is z direction for 2 points. So I'm gonna have 2 points here, z2 and p2, and then another point just below that is gonna be z1 and p1, and this distance is h between these two. And then the pressure at the surface is what we call P naught, is the atmospheric pressure. That is what we learned in the first lecture, right? Because if you are in the free surface of water, so there is no fluid, it's just an atmosphere. So you have just the atmospheric pressure, okay? So if I just write it down for this, I'm going to get P1 equals to rho GH plus P2, correct? This is from this relation here. So the pressure of P1 is going to be this, the pressure at P2 plus this rho GH, this the weight of this fluid above that, okay? And just note that if I rewrite this equation, H is going to be P1 minus P2 over rho G. So this is just going to give me the distance between these two. If I have the pressures, I can just estimate the vertical distance of these two, and this is called pressure head. Okay. So I want to make a very, very important point here, a very big point. So based on this formula, what we see is that pressure only for an incompressible fluid at rest only depends on the depth, not size or shape of the container. Because this is the only variable we have. We only have Z or H for the pressure variation. And as I said here, if you move horizontally from any point to another, the pressure does not vary and does not change in a fluid at rest. And so P only depends on the depth or Z. So this is a very important point, and I want to clarify that again. So here, pressure only depends on the depth, not size or shape of the container. So what does this mean? So it means if you have different shapes or size of the container, but if you have the same distance vertically, we will have the same pressure. So let's see. So let me draw two different container shapes with different sizes to illustrate this point. This is one thin container. It's a weird shape, but I know, but I just want to say it doesn't matter what is going to be the shape of that. And then here we have another one which is a little bit bigger, but with a curvy shape. So the shape is different, and also the size of the container is also different. One is bigger than the other one. And then we have filled these two with water up to a certain height, the same height. And this is a free surface, okay? So let me show it with this. These both are filled with water. Okay. And then I want to look at the pressure at this point for both fluids at this depth. So one is at point A, one at point B, and one at point C. And this depth is h is the same in all of them, the distance with the free surface. So let me write down. So PA, the pressure at A, and here we have the atmospheric pressure, or P naught, right, is gonna be this is the formula, right? P naught plus rho g times h. So I'm gonna have P naught or P0 plus rho g h. I just use this formula. So P at here plus this rho g h. And for PB, it's going to be P at here plus again rho g h. And for P at point C, it's going to be the same thing. It's going to be P at here plus rho g h. And P0 is the P at free surface, which is the reference atmospheric pressure. So from these, you see that P at A equals to P at B equals to P at C. They are all equal. Right? Very interesting point that the pressure only depends on the depth of the fluid and not the shape and the size of the container. And this is what we get from this formula here. Right? Because this shows for a fluid at rest, we have the hydrostatic distribution. That means that for an incompressible fluid which is at rest, the only parameter that really matters is the depth of the fluid, how much water or how much fluid is on top of that. And it doesn't matter where it is, because as we said, horizontally, if you move from one place to another, the pressures are going to be the same. So if I move here, the pressure is going to be the same. And if I move here or here in this fluid, the pressure is going to be the same. It doesn't matter where in the horizontal direction we are. And the only thing that matters is the depth of the fluid. Okay, so if the depth of these two flows, one here and one here, was different, for example, it was lower, then the fluid at B and C would be different than A. But now, because the pressure, the depth of the fluid in both of the containers is the same, so we are going to have the same pressure at A, B, C. So the pressure only depends on the depth and not the size. Like this one is bigger and this one is smaller, or the shape of the container. It doesn't matter how they are. The only thing that really matters is the depth, how much it is far from the free surface, the depth of the water surface. Okay. So this is a very important point that comes from this hydrostatic distribution that we learned. Okay, so in the next lecture, I'm going to solve some examples of this hydrostatic distribution, so you better understand how you should calculate this hydrostatic pressure in a fluid. And this is a very simple formula. It's a linear formula, so you can simply calculate it. P equals to rho g h plus P2 is plus P1. And this is what we got from writing the forces, the force distributions and forces on the fluid element here. Okay, so I'm going to solve some examples of that, and then we are going to talk about the barometers, how that measure the pressure in the fluid. and also solve some further examples about those. So most of the next lecture, I'm going to solve some examples so you see the problems for this hydrostatic pressure. And then after that, we are going to go toward more complicated shapes and geometries. For example, a slanted plane or on a inclined plane, and then other types of problems that can be kind of solved in this context. Okay, so the formula is very simple for the hydrostatic pressure because we don't have acceleration, and we will just see the examples and problems that this formula entails in the next lecture. Okay, thank you very much, everyone.